things to do. um, First things first this morning. Good morning. Hello. Day 4. Here we are, day 4, block 7. This is usually about the right time for a pep talk. This is about the hardest part of our curriculum conceptually. It's the biggest jump, right? Like 211, 212, 213, 214 are all like big concepts, one right after the other. And there's a lot there. So, excuse me. So a couple of things I want to remind you of as teachers taking this course. First of all, you are going through this course roughly at 180% speed. That's about how fast you are going through this, right? You have a lot less hours than your students will. Not only that, your students get an hour of content and then they get to like absorb it and go home or whatever the case may be. If you're on a block, 90 minutes, right? And then they get another block and then they get to absorb it. But you don't have that benefit, right? It's one right after another. Not to mention, of course, that you have like, lives and things happening outside of this training. So one of the things I want to remind you of is that this is a very difficult undertaking that you are working on. And so struggle is not only okay, it's likely. It is a tough situation to find yourself in. Many of you are struggling. And so even if you feel like you're the only one, I'm here to tell you that you're not. In fact, I struggled with this training. I took this training just like you guys are taking this training. Sorry, my monitor is tilting. And I struggled with it too. Ooh, man. And that was those were 8-hour sessions and then, homework after that and whatever. I struggled with it too. So that is expected. It is normal. It doesn't feel good. I'll give you that. But that's a kind of a side effect of growth, right? Growth is uncomfortable. It hurts when, we're growing and we're learning and we're getting better. That's sort of going to happen. The other thing that I want to remind you of is that your expectation cannot be of mastery. You will not be a master of this content by the end of next Friday. That's just a reality of what's happening, right? I want you to be excited about it. I want you to enjoy it. But it'll take you some time to get used to it and get comfortable with it. There's a lot of stuff in this curriculum, and 2 weeks just isn't enough time to become a master on it. Nobody's going to pay you to take a 6-week training, every day and everything else, but that probably would be appropriate, right? But that's the long and short of it. When I took POE training, I didn't do well with some of the topics in POE training. Those of you who taught POE, like there's these truss calculations. You have to figure out, the stresses and strains on the members of a truss. Man, I was really bad at it. Fast forward, a couple of years, and now I really like it. I really, I figured it out and I feel comfortable with it. And that's what I'm, where you guys will get. But I just want you to remind you that this is a reality of this training, is that it goes too fast. It just does. It goes too fast. There's nothing to take out as far as I can tell. I've taken just about everything I can out of the training. So there's very little busy work at all. I don't know if there's any busy work, but it's just sort of a reality of this training, is that it goes too fast and it's uncomfortable, but that's where we are. Okay. You'll get through it. I've never had anybody fail this training that didn't, choose to do so. If we get into next week and you're like, man, I need a couple more days or something to really get through and finish all of the submissions, you can talk to me about that and we can work it out. Okay. I have to put some paperwork through with Project Lead the Way that just says like, this person's going to need a little extra time. It's cool. Don't close the books on them yet. They're working. I vouch for them. They're getting things done. They will be okay. And so we can take care of that kind of stuff. So, don't get super duper duper crazy stressed about it. This weekend, if you have some time and you want to, play catch up a little bit this weekend, that's certainly an option. I think I was telling somebody, block 9 and 10, which is how we end this week. I probably won't grade them till Monday at all. So like, if, don't feel like you have to get them in Friday night or anything. Don't worry about it. Okay. Okay. That's my pep talk. That is going to be fine. It's going to be great. Everybody in this class is doing well. I've people who have been doing significantly worse than you guys are in here have passed the class, gone on to teach it and love it. So I think you guys are going to be great. Okay. All right. Now, anti-pep talk. Crash is not keeping up pace like I need to. There's two things we didn't get a chance to talk about yesterday because I ran out of time. And so we need to cover that today. I told you guys, block 6 submission. I told you not to worry too much about turning that in last night because there's some more stuff that I wanted to cover on block 6. Okay. There's two theorems that we didn't really get through yesterday that we need to talk about. Okay. So I want to start with that today. No, that's not true. Before we start with that, what came up in block 5 or 6 yesterday was the idea of a 3-input gate. Okay. Because one of the activities goes draw this circuit and then draw it again using only 2-input gates. Well, first of all, a lot of kids read that as only 2 gates, which is impossible. You can't do it with only 2 gates. But they mean 2 legs, 2 inputs. So if I open up Multisim here, every gate that we've done so far, like 74LS08, for example, has 2 inputs, is 2 legs on it. But let's see if I can remember 74LS11, I think. Yeah. So this is 74LS11, and it's a 3-input AND gate. And so all 3 legs have to be 1 in order to get a 1 output. So this is a thing that does exist. It's a real thing. And if I had an expression, like A, B, C, for example, I could put my A on one leg, B on the next leg, and C on the next leg, and I would get it with 1 gate, as opposed to what we've been doing, which is cascading gates together. So we would be, instead of that, we would have done A and B and C. This is what I showed you to do. A and B and C. Now, while this top one looks more efficient, maybe at its first glance, there's some engineering issues. Okay. First of all, this chip is about 6 times more expensive than this. This gate, let me rephrase. This gate is about 6 times more expensive than this one. Okay. Mostly having to do with like economy of scale and that sort of thing. But yeah, this gate's about 6 times the price of that one. And so this scenario is actually significantly cheaper than that one. So like right off the bat, this is a more expensive solution. And there's some things that we're going to do later on that, like for simplification and those sorts of things, that this bottom one's going to kind of work out better anyway. So generally speaking, if we are going to build this thing, if this is going to be an actual product, I would almost never use these 3-input gates if I can avoid it. Okay, I don't even stock them in my classroom anymore. For a while, they were included with the kits that you guys got, but I don't even bother with them. So I'm to the point where I don't even really talk about 3-input gates at this point, and I didn't with you guys. So, that's shame on me. I should have said something. I don't really talk about these until a little bit later in the curriculum. Next week, we're going to talk about this programmable chip thing, this S7. You guys don't have this yet, but it's in your classrooms. And in there, it's a little bit like, made up Fantasyland in terms of the components that we put in there. And everything costs the same because it's made up in Fantasyland, right? And so when we do that, I'm like, hey, use a 3-input gate, use a 4-input, use a 10-input gate. Who cares, right? It's all made up. So it doesn't really, there's no real issue with that.
Question.
Okay? Yes.
So like in multi-sim, the 3-input looks like a more elegant solution. But if you were real life building this, there would be 4 on the chip anyway, right?
Correct.
The other ones, so it would all be one chip.
Yeah. Yes.
Whichever way you did it, it would be
Yes.
one chip. It would look the same.
Yeah. Correct.
What is the difference between the D at the end of the ID and the S? Like when you go into multisim?
Oh, the letter at the end has to do with the physical package of the chip. So like whether the legs go straight down or whether they're splayed out to surface mount onto a board. In other words, for us, it makes no difference whatsoever. But that's what that letter is. It's about the physical, like what is the physical shape of the chip? Good question. Okay, so that's the 3-input thing. So if you see in the curriculum, if ever they're like, build it and then build it with 2-input gates, well, my kids and everything, usually we just jump right to 2-input gates because we don't like busy work, we don't like repeating work. We just go from there. Okay, so that's the 3-input gate thing. There are like, for some bizarre reason, I think it's got like, oh, maybe they took it out. They have like an 8-input, like look at this monster here. They have some crazy things in here. But for the most part, we use just these cascaded gates. Okay. So that was the first thing. All right. The next thing is the theorems I didn't get to yesterday. Let me share my iPad. So the last theorem, I'll ask for your forgiveness here. I call this theorem 13 because that's what it used to be called. And then they changed the numbering, they being Project Lead the Way, changed the numbering on these theorems. And I have been doing it for a long time, so I got a bad habit. So I'll probably call it theorem 13 by accident a couple of times. But what this theorem actually, I actually more often call it something different. And I hearken back to Jurassic Park. I don't know, you guys ever seen the original Jurassic Park, not Jurassic World? You guys seen the original Jurassic Park? Anybody seen that movie? All right. I'm actually surprised how many of my students now have seen the original Jurassic Park. But anyway, so in the original Jurassic Park, for those of you who haven't seen it, there's a guy describing how velociraptors hunt, right? And he's talking about you see a velociraptor, you see the raptor across the clearing, and you're like not moving because you think maybe the vision is based on movement. You're like locked eyes and nobody's moving, and then just then the other raptor attacks you from the side that you didn't even know you were there, right? And then that's a little foreshadowing for something that happens later in the movie. This theorem I call the raptor theorem, because when you are doing a Boolean simplification and you think there's nothing else you can do and you say this is as simple as it can get, it's probably the raptor. You probably missed the raptor. The raptor theorem is the one that you probably missed, right? So when we're working through these things, you say, Crash, I can't figure out how to get any more. I'm like, it's probably the raptor, right? So that's the theorem that you probably missed. Now, Project Lead the Way calls it the consensus theorem. If you Google this, you will find different stuff. The consensus theorem is not necessarily like a generally adapted term for this. And to my knowledge, I don't know that there is like a good separate term for this other than just this is one of the Boolean theorems. These numbers, by the way, that's a Project Lead the Way thing, right? So don't go to college and be like, oh, I love theorem 17. Like they're not gonna know what you're talking about. This is just a Project Lead the Wayism. So if we look at theorem number 16 here, 17, 18, and 19, they're all actually the same theorem, just like ever so slightly modified. Where's my pen? So if I look at this, I've got X or X naught Y. And what happens is in this exact format, it ends up dropping the X naught. It ends up dropping whatever's connected to this second term, it drops that. So this X naught gets dropped here. So X or X naught Y, the X naught gets dropped. Okay.
Is that only because it's the two, it has another X in there, so they almost, so is that X stays though, but that X not drops just because that other X, or that just drops out just because it drops out?
Well, it drops out because that's like what the theorem shows.
Okay.
If later we want to derive it, we can, but suffice to say that because this is a theorem, these are equivalent. Okay. Now if I look at theorem 17, it's the same thing. X or X naught. The only difference is that this is a Y naught. It was Y over here. It was a Y naught over here. It's the same thing, right? These are these two. Let me zoom out a little bit. 16 and 17 are the same thing. The only difference is that this is a Y here. It's a Y naught there. A Y here. A Y naught there. It's like the same as if I said this was a R and this was a L, whatever. It just gets carried over, right? Theorem 18 is the same theorem, except for this time the X naught's over here. X naught or XY. And you're left with X naught or Y. So like my cheat for this is if you put it in this format, you're going to keep the term that's by itself and then the different one, right? The two outside ones. Term that's by itself and the different one. You're going to keep the term that's by itself and the different one, right? That's what you're left with. Here we've got X naught or XY naught, keeping the term by itself and the different one in your output. So I don't really know why they split this into 4 theorems. To me, that's unneedingly confusing. So to me, that's one theorem. Right, that's one theorem. And they used to call it just theorem 13. Or the Raptor theorem. That's what we call that. Okay. Now here's a great thing to show the kids. I'd say, all right, cool. So then real quick, which one of these is that right there? Is that 16, 17, 18, or 19?
$16.
16. Oh, but it's an X naught here.
Oh yeah.
It's not an X naught.
None of them.
None of them.
One from yesterday.
I can tell it's too early for trick questions. But yeah, it's none of them. It's not 16, 17, 18, or 19. This is not a Raptor because it's the same. This is the same term, X and X. And every single one of these, one of them's got to be X and one of them's got to be X naught. X, X naught, X, X naught, X, X naught. Here it's not. So this is not, even though it looks like it, and it's confusing because kids see that format, and they're gonna be like, "Oh, that's a Raptor theorem." No, it's not. What I would do with this, while we're talking about it, Laura said this is like something you'd see from yesterday. Yeah, what I could do is I could take X out of both of these terms. Like when you see this normally, if you saw just this, you'd be like, "I'm done. I can't do anything with that." But this we can do something with it. X or XY, we can take X out of both of those terms. When you take X out of X, you're left with a 1 or Y. So I took X out of both of those two terms. And then this is a theorem. Anything ORed with a 1 is just a 1. And anything ANDed with itself is itself. So that just becomes X. So just as soon as people get this Raptor thing figured out, they're like trying to apply it to everything, but this is not a Raptor. These two letters have to be opposites. So that's my theorem, my Raptor theorem, my 16, 17, 18, 19. let me grab a problem from the course so we can do one together. So the way that I'm mostly, as I'm pulling this up, I'll talk, the way that I'm mostly attempting to solve Boolean, okay, is I am doing theorem 1 through 9s, the ones I showed you yesterday. That's my first go. Like first thing is, can I find any easy ones? It's theorem 1 through 9s, especially like numbers. Like if there's ones or zeros out there, oh man, that's low hanging fruit. I'm going to do that. That's my first thing. And then once I run out of those, then I'm looking to distribute or factor things out to make theorem 1 through 9s or these raptors, right? And then I think that's the thing that comes with like practice and working with these a lot, is you start to see like a step or two ahead. Like, oh, if I take T out of this term, you know, I'm gonna be able to get a raptor theorem. I'm gonna be able to get a theorem 7 or whatever. Probably not by number, right? You're probably not going to be like, oh yes, clearly that's theorem 4. But you'll start to kind of see those patterns. All right, so the problem in the PowerPoint after our consensus theorem. Where the heck is it? There we go. All right, so they've got PS or P Q naught S naught or P Q S. Okay. So the first thing I'm going to look for is theorem 1 through 9s. Like, is there any 1 through 9s here? I would say no. By default, there's no theorem 1 through 9s there. Okay. And there's not any clear consensus theorems there either. So I'm probably going to need to factor something. I'm probably going to take something out, right? That's what I'm going to want to do. And I've got some different options here to do that. So I'm going to take a P. I'm going to take a P. I'm going to take a P out of some terms. Now, some of you probably would be like, let's take a P out of all 3 terms. You can do that, but I'm going to caution you against it. Just from years of experience, I think when you do like some multi-nested parenthesis thing going on, it's really easy to lose the forest through the trees, so to speak. So I always encourage kids, just attack 2 terms at the same time. Just pick 2. All right. Don't try and do 3 or 4. When people do the majority vote simplification, they're like, I'm going to take P out of 7 terms here. And inevitably something gets lost. So I'm going to pick 2. So I'm going to pick these first 2. I'm going to take P out of these 2. So I'm just factoring that out, and I'm left with S or Q naught, S naught, or P Q S. I just distributed. That's all I did. I can't take S out of this because one's an S and one's an S naught. S naught. It's not. All right. You see anything? What can we do here?
Lost 17.
A raptor theorem?
Yeah.
A raptor. Okay, so 17 says X or X naught, Y naught. And up here, I've got S or Q naught, S naught. So that's not the exact same layout, but is that the same as
Yes.
Are those two things the same? Yeah. And just to prove it, remember our commutative law says that's okay. You can change the letters. So if I really wanted to prove the point, I could say, yes, theorem 10 says that I can just swap these two letters. The order doesn't matter. Again, I don't make kids write those theorems down, but just because I wrote it, I had to do it. So this is a Raptor theorem. There it is. Okay. So S plus S naught Q naught gives me the outside two terms. It gives me the term by itself and the different one. So I'd be left with S or Q naught. Thanks to theorem number 17, Zach told us. Okay, cool. I then immediately put this back in. I distribute this back in. I don't want to deal with parentheses, and that's confusing. So I'm going to put this right back in. PS or PQ naught or PQS. Just distributing it back in. Really, it's 15, whatever. What should we do now?
If, I don't know if this is gonna lead anywhere, but if you take PS out of the first and last term,
Okay. And by the way, Gabrielle, something I like there. You know, I don't know if it's going to lead someplace. And I tell you this all the time. Like, as long as you don't break any Boolean rules, try it. Right? Maybe it won't be helpful. Maybe it will. Who knows? We can always go backwards if we need to. So Gabrielle says, let's take PS out of this term and this term. If I take PS out of PS, I'm left with 1. Or over here, I've got PQS. I'd be left with Q. We're just factoring there. Okay. So 1 or Q, I feel like that's a theorem. That's right here. Anything ORed with a 1 is a 1, thanks to theorem number 6. That seems pretty productive. And then anything ANDed with a 1 is itself, thanks to theorem number 2. And I think we might be done. I think that's about as simple as it gets in SOP form.
So if you continued and distributed the P out, that would be POS form.
Correct. Yeah.
Okay.
If I said P, S, or Q naught, that would be POS form, which is fine. But I think the problem in the PowerPoint, like, it's like make it SOP, so we know it ends here. Okay. So that's our consensus theorem, our Raptor theorem. Okay. The other theorem we're not going to run into as much. But somebody asked the question. They said, you know, if I have X not Y or X, Y not, do those Do those like cancel each other out? You know, is that like x naught plus x? And the answer was no, it's not. It's not that. And I believe somebody asked, is that like x naught or x? You know, is that, let's see, is that theorem 8? This right here, is that theorem 8? The answer is no. That's not theorem 8. What would, if I wanted to do this and have it actually be theorem 8, you know, it would have to look like? It'd have to look like this. Now that's a pretty subtle difference. I've got the bar going all the way across XY. Here, I've got X naught, Y naught. So I want to unpack that here briefly because that informs our last theorem. So what this would look like, X naught and Y naught, that would look like an AND gate with two inverters feeding into it. That's what that would look like. X naught, this thing right here would look like X naught and Y naught. This would be X and Y with an inverter after it. So first of all, these are like physically two different things. And we're going to look at a truth table real quick and see what this would look like. So X, Y, Z, 0, 0, 0, 1, 1, 0, 1, 1. Same thing down here, X, Y, Z, 0, 0, 0, 1, 1, 0, 1, 1. Okay, so up here, if I put 0 and 0, it's my first row, 0 and 0, they both get inverted. So I'd be looking at a 1 and a 1 here, going into my AND gate. A 1 and a 1 and an AND gate would give me a 1 output. If I had a 0 and a 1, that would turn into a 1 and a 0. If I have a 0 on an AND gate, the output's definitely 0. Either of these legs is a 0, the output's 0, which means this is a 0, and while I'm at it, this is a 0. And if I put 1s on both of these, X and Y, they both get inverted to 0s. I got 0 and 0 going into my AND gate. This is a 0. So that's what this does. Let's look down here now. If I put 0 and 0 into this AND gate, I would get a 0, which would get inverted to a 1. So far, so good. They're the same. Now, if I put a 0 and a 1, I would get a 0 here, which would be a 1 here. Uh-oh. And if I put a 1 and a 0, it becomes a 0. It turns into a 1. And if I put a 1 and a 1, it becomes a 1, which gets inverted to a 0. So not only are these physically different, they evaluate different. They're literally different circuits. X naught and Y naught is very different than X and Y not. Okay. Now, Augustus de Morgan is a Frenchman. Augustus de Morgan observed this and was playing around, I guess, and was like, I wonder what X naught or Y naught. Let's see what that would look like in a truth table. So what he figured out, he did his work and he said, okay, so X naught or Y naught would be 1, 1, 1, 0. And he's like, wait a minute. I've seen that pattern before. 1, 1, 1, 0. That's the same as this one. That pattern, this pattern, same pattern. So Augustus de Morgan noticed that X naught or Y naught was equivalent to X and Y naught. That's what he found out. And fast forwarding the tape a little bit, he also found out that X or Y naught, the bar over the whole shebang, was the same as X naught and Y naught. And what I've just written is the last theorem. This is, they call it the De Morgan's theorems. These two right here, that's what they are.
So when you're building these, like if it's a line over each individual letter, that means it's inverted before the gate.
Yes, correct.
Whole line means you invert after the gate.
Yes, well said. Now, one of the reasons De Morgan, I mean, other than just being like neat, one of the reasons this is helpful to us is when you see a bar over like multiple things, it's almost like parentheses, in that you can't really like sneak in and grab. Like if I wanted to get this Y out of here or something, like let's say I had something like that, and I wanted to like factor out the Y or something, I can't because it's in this thing over here. It's like under this bar. It's kind of like a parentheses. I can't sneak in and grab that. So bars over multiple things makes Boolean harder because you can't like get in and get the things you need and pieces of these things out and grab letters. So really the bar over multiple things is not good for us. We don't like that. So what De Morgan's theorems give us is they give us the ability to break these bars. Okay. And in fact, they got a nice little clever little saying in there, little rhyming saying. And they say, well, De Morgan's, you're going to break the line and change the sign. Break the line, change the sign. So if I have, for example, this, I'm going to break the line. I'm not going to delete the line. Be careful. I'm not going to delete the line. I'm going to break it, break the line, and change the sign. So I break the line so that there's a bar over X, bar over Y. The line is broken. And I had a multiplication sign, but I'm going to change that to an addition sign. Break the line, change the sign. Okay. That's De Morgan's theorem. Now in the activity 215, I don't know if you guys tried it last night or waited or whatever. You're going to see some frankly fairly impractical, unrealistic examples of De Morgan's theorem. They just like, so they have math problems to do. They give you like these ridiculous, like, W, X, Y, Z, and there's like a bar and a bar and a bar and a bar, or something like that. That is not something we're going to typically see. That is pretty unusual to start with something like this, but they just want to give you practice De Morgan's, which is why they give you some kind of ludicrous examples to work through.
Could you say that one more time? So just because I was looking at that question, how do you go about that again?
So for this one, if I was going to do this one, so really the way I would do it is I'd break like one line at a time, first of all, and I'd start at the top, right? I don't want to stay down here. I'm going to start at the top. So this is the first one. I'd break this one right here. And I would have W, X, Y, Z. I'd have Z has a bar over it. And then W, WX, WXY. And then you still have this bar up top, right? Like this one broke, but it didn't delete. So we'd have that there. And again, Tyler, I'm not sure if I copied it. I'm just going from memory. I don't know if this is exactly how it looks, but these two bars are the exact same length. You know what that means? It's time for my favorite theorem, theorem number 9. So when I have two bars that are the exact same length, boop, just get rid of them. Anything not is just itself. So I can get rid of those two bars and I'd have W, X, Y. I didn't, you know what I didn't do is I didn't write in my sign change here. This is multiplication. So I got to change the sign. Really common errors. Kids forget to bring down, a bar, forget to change a sign. Really common. And then you can break the line, change the sign here, and keep kind of whittling your way down. For 2 and 4 and
Thank
2 and
you.
5, by the way, yeah, absolutely. For 2 and 4 and 2 and 5, by the way, as you're working through them, please don't hesitate to look at the answer keys so you can kind of, look at yourself, check yourself while you're doing it. I'm the kind of person I can't look at the answer key ahead of time. Otherwise, I can't form my own thoughts. So I would have to try it on my own and then check the answer key. That's how I work. All right, we got to do number 6 on the homework. Because man, it is super difficult. Okay, so there's 2 ways to do number 6. There's the easy way and the hard way. And to do it the easy way, you need De Morgan's. And if you teach this class exactly as it is written, kids don't know how to do De Morgan's when they do number 6. So technically, they would only be able to do the hard way without De Morgan's. When I teach this, depending on timing, I usually go ahead and teach De Morgan's in the same lecture. So kind of like I did with you guys here, I would finish the Raptor theorem and then just go right on to talk about De Morgan's, even though technically it's a separate activity, separate PowerPoint. To me, I don't see a whole lot of point in separating them. So this is number 6. First thing I do is theorem 1 through 9s. That's the easy. Okay. And I do see a theorem. I see JK or JK. I see something ORed with itself. JK or JK is JK. Get my theorems back here. Anything ORed with itself is itself, theorem number 7. So JK and JK are just going to be JK. Okay. And then we would probably factor that back in. And then we'd say, all right, so I could take a J out of, no, there's not, can't take a J. I could take a K out of, no, I can't take a K out of anything. I could take an L out of these two, but that would just bring me back one step. That would just bring me, that would undo the step I just did if I took an L out of these two. And so most of your kids, Mike Crash included, would be like, I guess I'm done. I guess there's nothing more to be done here. But you can get a little bit simpler here. Now, in my 16 years of teaching this class, 14 years of teaching this class, 10 years of teaching it to adults, I've never seen anybody come up with this solution on their own. So I just want to give you an idea of how much of a kind of a mental stretch this is. So when you see a problem where it really looks like something should, like you have a bunch of, I got J's and J knots, I've got K's and K knots, I've got, it feels like something should counteract here. There is a little something we can do. All right. Now, in order to do this, I need you to afford me a little grace here. Okay. That the theorems, they work forwards and they work backwards. Right. So, anything ANDed with a 1 is itself, which means in theory, I can AND something with a 1 and get away with it. So, right. So like if I had K and I decided I'm going to do K and 1, that's okay, right? Can I do that? You guys okay with that? I just add an and one to a term. Theorem 2 says that's okay. Anything anded with a 1 is itself. So in theory, I can and something with a 1. And it doesn't hurt anything. You guys okay with that? Kind of, sort of? Okay. So any of these can work backwards. And so here's what we're going to do. Here's what we're going to do. We're going to take this middle term here. And I'm going to and it with a 1. Theorem number 2 says I can do that. Theorem number 2, I'm going to write reverse. Not that I need to, but just so we're like, we remember. We're like doing theorem number 2 in reverse here. Okay. Now this is really weird. Theorem number 8 says anything and ORed with its inverse is a 1. So in theory, I can replace a 1 with this x or x naught. So what I'm going to do is I'm going to replace a 1 with k or k naught. Is that allowed? Theorem number 8 says it is. So I'm going to replace this 1 with k or k naught.
Is there a reason why you chose K to be K1? Or is it just like the random letter that you chose? Or is there any
Up here, I just picked a random letter.
just pick the random letter? Okay.
Yep, this is just picked a random letter. Mhm. Thanks for asking. Okay. Now I'm going to stop with those shenanigans. And I'm going to do regular stuff from here down. Okay. No more weird shenanigans. So I'm going to distribute that back in. So JK or J naught KL or J naught K naught L or K naught L. Just distributing. Ooh, hold on. These look like they connected. Let's get rid of that. Make sure they don't look like they're connected. Okay. Okay. Now we're gonna do something here. One thing, 1 out of 5 times when I do this problem, I start to take J naught L out of these middle 2 terms and I accidentally take a step backwards. Don't do that. You can do whatever you want. Don't take J naught L out of these 2 because that's what we just did. So I don't know. What should we take? What should we take? We want to take we take K out of the first 2. We could take K naught out of these 2, whatever you want to do. We'll take K out of the first 2. Why not? So take K out of the first 2, and we're left with J or J naught L. We're just factoring out there. J plus, excuse me, J or J naught L. What's that? It's the raptor. It's a raptor theorem, right? So J or J naught L is like X or X naught Y. That'd be our theorem 16 here, our raptor theorem. And like I told you, I always factor right back in. I don't want lots of parentheses. It makes me uncomfortable. So I'm gonna put this right back in. It's JK or KL or J naught K naught L or K naught L. Okay. Let's see. I can take looks like L. Take L. Maybe I'll take L out of the second and the fourth term. K or K naught becomes a 1. Makes the theorem number 8. Anything ANDed with a 1 is itself. Thanks to theorem number 2.
Just be, I wrote it differently. I did KJ instead of JK, but based on our theorem, that's okay to have the letters reversed, correct?
Absolutely. And thanks for pointing that out. Yeah, absolutely. That's fine. I'm going to take L out of these two terms over here. And if I take L out of L, I'll have a 1. Or J naught, K naught. Now this is interesting. The theorem I was going for was theorem 6, which is that anything ORed with a 1 is a 1. Now this doesn't quite look like that because I have two letters over here, J naught and K naught. Is this theorem 6, even though there's two letters over here? Randall's nodding. Yes. Randall, you feel good about that? That's the theorem 6. Yeah. And he's right. That's okay. We can kind of treat this as X. So yeah, theorem 6 says that these will just become a 1. No, hold on. Hold on. Forgot to put in, this is factoring. Okay. Theorem number 6 down here. And finally, anything ANDed with a 1 is itself. Theorem number 2. Sorry, I ran out of room down here. JK or L. Now that's the end of it. Okay. Now, gross. And like I said, I would never expect a kid, an adult, anybody to be like, clearly, I'm going to do these two theorems in reverse, and I'm going to put this K and K naught back in, and blah, blah, blah. It's going to allow me to get to here. No. Okay. And I've actually, like, philosophically over the years, I thought maybe we should just take this problem out. But I actually like that it's there and I can talk through it with the kids and, you know, be like, there are situations where like you may not see this, but there is like, you know, a simplification to be done. I'm straight up, I'll tell the kids, like, I don't have the brain to see this. I bet some people do. I bet some people have the brain to be like, yeah, I looked at this and I thought there must be something I can whittle out of this. And maybe if I try that, then, you know, I can make it happen. Now, when you guys do the majority vote simplification, this situation can happen. I'm going to tell you how to avoid it, but your kids are probably not going to listen to you like they wouldn't listen to me and run into a problem. So knowing that this is a possibility, I think is a good thing. Okay, so that's the hard way to do it. Can I show you the easy way real quick? The easy way to do it. So the easy way is with De Morgan's. If you guys will allow me to be lazy just for a second, I would do the exact same first step. So on the next page, I'm going to copy just this line right here. You guys okay with that? Is that all right? I'm going to copy just this second line because that's where I would start. If I was doing it the easy way, I would do this line to here, and I would start here. So it's JK or J naught or K naught L. Now, what we did last time is we distributed this L into these terms and, then did all that craziness. But we just talked about a bit about this, didn't we? J naught or K naught. We were just talking about how that's really different than J or K naught. And that led us into this whole De Morgan's conversation. So J naught or K naught, De Morgan's tells us that's equivalent. J naught or K naught tells us that's equivalent to J or K with a naught over the whole thing. So I'm going to convert this to that. I'm going to run De Morgan's here and say, all right, so the De Morgan says that's J, K with a bar over the whole thing. I could put these parentheses here, but they not really necessary, but put them there. So that was De Morgan's. I don't even know if they have a number on De Morgan's. I guess it's 20. Now this, I don't know if you can see it. I don't know if you see it coming through the clearing, quietly moving the brush out of the way. Claws sharpening. What theorem are we looking at here?
Is it 16? I'm not sure though. No.
16, I'm just gonna write over here. 16 would be X or X naught Y. JK naught. This is the exact opposite of this. So if this is X, this is X naught. Yeah, I'm with you. So this is a raptor theorem. So just like the other raptors, I would take the term by itself and the term that's different. You know what? We're done. If you remember all that mess on the other page, we landed at JK or L, and that was the end of our simplification. So Boolean or De Morgan's isn't always like such a magic bullet. They kind of cherry picked this example, but boy, it was pretty nice to have it right there. It went from like, I don't know how many lines it took us on the previous page, like 16 lines to 2, 3. It was pretty sweet. Okay. Question.
Yeah. So you said that not J and not K or not K is the JK under the bar. That's just a theorem, De Morgan's theorem itself, right?
Correct.
All right.
Yep.
Question.
Yes.
Would that fall under 8 too, or is that not work at all?
If the L wasn't here, it would. Yeah. If this
Okay.
L wasn't here, you could have said that this or its exact opposite. Yeah, that would have been a theorem 8. But because this L
Okay.
was stuck on there, we couldn't theorem 8 it.
Okay, all right.
Good eyes. That's right. If you saw that, that would be awesome. Okay. We need to take a break. And then I'm going to do majority vote simplification when we come back from break. I'm going to walk through it just with you. Okay. So let's take a 5-minute break. Come back at 9:06. Oops. Just realized I didn't resume recording. And theorem number 2 says PVN1 becomes PV. Okay. Bring the rest of the stuff down. PV naught S or PV naught S naught T or P naught VS T. I, as a teacher that knows where this is going to end up, I'm starting to see the bones of what this will end up being. PV is here, president, vice president. This right here, PV naught S, I bet that's going to become PS eventually. I bet that's where that's going to go. And this is probably going to end up being PT. I still got some work to do, but I can start to see it vaguely where it's going to become. I don't see any more easy 1 through 9 theorems. I've kind of exhausted all the low-hanging fruit, and now I gotta do things that are a little bit more complex. So let's do these two here, these last two. Let's take P out of these two. I'd be left with V naught S or V. What's this? Is this anything? V naught S or V? What if I rearrange it? Theorem 10 says I can rearrange letters. So what if I rearrange it and say it's V or V naught S? I just rearranged them. Is that anything?
16.
Yeah, that's a raptor theorem. That's the raptor. So that would leave me with V or S. I always put that right back in. Parentheses make me uncomfortable. Note, I have stayed away from this P naught like it was the plague over here. I haven't touched it. I didn't move anything. Leave that P naught alone over there. All right. So if I look at like these two terms, I could take like T out, but that doesn't really help me because the P's are different. The V's, and that doesn't really help me. So again, I think I'm gonna leave this one alone for a while. What can I do with like this and maybe one of these? These look pretty good. But what can I do with this and PV or PS? What do you want to do? Let's try something. Somebody give me a suggestion. Can I take V out of these two terms? No, because this is V naught and this is V. I can't do that. Can I take S out of these two terms? Nope, because this is S naught and this is S. So I think pretty much my only option is to take P out of one of these two.
Could we do what we just did? Just have more letters, if that
Okay.
makes sense.
Yeah.
So we
Which
pull
one
out
do you want to?
the-
Which one do you want to do?
The PV right there.
So PV, you want to take P out of those two. So that would leave me with V naught, S naught, T, or V.
And then we can do the same thing with that number 16, V naught and V.
Okay. All right. I love where you're going with this, Caleb. I had a math teacher tell me once that when you go from the bottom of the whiteboard to the top of the whiteboard, you should never do any operations because people lose them. I'm going to need to go to a new piece of paper here. And so I'm going to use that rule. I'm not going to do a new operation. I'm just going to recopy this on the next page. Okay. So this is P naught VST or P V naught S naught T or V or PS. And that was just a recopy. So Caleb says, if I'm understanding him correctly, he's seeing a raptor over here. He's seeing a possibility of a raptor theorem. So let's move, let's just see what we can do to see if it's any clearer. So if I rearrange it and I say, okay, so V or V naught, S naught T, I just rearrange the letters. And I think this is hard for a lot of people to see. Call it theorem number 10. I just rearranged it. Okay. So is this a raptor? And the answer is yes. Caleb is right. This is a raptor theorem. In, our raptor theorems are usually X or X naught Y. So here we got V or V naught. But there's two letters here, Crash. Yeah, I know, but that's okay. We could consider this to be Y. This S naught T. We can consider that to be the Y in the consensus theorem. So this is a raptor. So it becomes V or S naught T. A lot of people get tripped up there. Not sure. It doesn't seem like it's a raptor theorem because of this extra letter, but it is. Okay. Distributing back in. Whoops. PV or P S naught T or PS or P naught VST. Hold on. Let's, that was theorem number 16. And we just distributed back in.
So I don't know if it's correct or useful, but like when I was looking at that one, sort of the way my brain looked at it as imagining, the implementation of the circuit, that that P V naught S naught T or V is telling me that if V is triggered, it's going to output regardless of what the others are doing.
Mm-hmm.
So that V naught condition is redundant.
Mm-hmm. Yeah, that's a good way to
Right.
look at it. Mm-hmm. Okay, I'm guessing like 2 or 3 more steps here and we're done. So this PS naught T and this PS, I think we can do something with that. If we take the P out of those two. It's another one of those raptors. Again, it's not quite in the right order, but S or S naught T, that's a consensus theorem. So that would leave me with S or T and distribute it back in PS or PT or PV or P naught VST. I have so many kids stop here. It's kind of funny. Like I have a conversation with them typically like I have with you, like, okay, we can intuitively figure out what we think the most simple form is and blah, blah, blah. And we talked about PT plus PS plus PV plus VST. We talked about that. And yet they land here and they're like, done. Like, wait, if vice president, secretary, and treasurer all vote yes, who cares what the president thinks? Right. So we know intuitively that this P naught has got to go away. Doesn't need to be there. So sometimes I'll joke around with kids and say, I'm going to show you a magic trick. Pick any term. Pick any term over here. PV, PS, PT, I don't care. Pick whichever one you want. Right? Because the next step's going to work regardless of which one we pick. So I'm going to pick PT. I don't care. Doesn't matter. And I'll take PT. And this term, finally, I'm going to mess with this term. I haven't touched it. 25 steps in, I haven't touched that one. Finally, I'm going to mess with it. I'm going to take T out of both of these two terms. That's all I can take out. And I've got P naught VS or P. And that's another one like Caleb was saying, this is a raptor, even though it's got like an extra letter on it. That's still a raptor, right? If I rearrange it, it's P or P naught VS. Right, just rearranging.
So you're gonna drop that P naught, right?
Correct.
Now, just because like I feel like there's a pattern to it when you're doing that that combination right there. When you see that, you have to show all your work, but if you see that coming, you can make that jump or no. Because like, you can kinda see that.
I would tell my kids to show every single step because they're learning. Now, if I'm doing some, Boolean on the side just for funsies, I probably wouldn't show every step. I'd see, yeah, okay, I see that, I drop it and I know where it's going. But because we're learning, I'm a big stickler about they got to show everything.
Yeah.
More often than not, your job as a teacher is they end up with like, they get to some step and they're like, all right, here's what I got. PT or V naught ST. And I'm like, no, you made a mistake. You made a mistake somewhere because this is not correct. I know, because this is where it's going to end up. If this is all you have, you made a mistake someplace. So let's go back in your steps and say, how did you make this jump? How did you make this jump? How did you make this jump? Oh, that you thought this was a theorem 16, but it wasn't a theorem 16. Then you can kind of walk it back. That's why it's such a huge deal to make them do it now. Okay. So you have now, I walked through it. You have a way to do it. Like I said, this is not the only way. You certainly could have made other choices along the way. You could have picked different things to take out. You could have, looked at different options. There are many different ways to solve this problem. Okay. But I will say this is, I guarantee you, the simplest SOP form expression. So that I can tell you with absolute certainty. So if you end up with like something simpler than this, and you're like, look at me, I did a thing. No, you made a mistake someplace. I can tell you with absolute confidence, if you don't have this, you've made a mistake somewhere along the line.
So how would that look like how different is that from the product of sum form then?
If I took, for example, P out of these three.
Yeah.
This is P here. So I would have like VST or P and the quantity V or S or T. Like that would be POS form.
Okay, thank you.
Mm-hmm.
What is the rationale in the very, very beginning? Because I know I'm going to have that student that's going to say, why do I not touch the not P? Is it just because it looks so different and from doing problems over and over, or like how do I
the reason is, I mean, Normally, all I have to tell them is that that's going to make it more difficult. They're like, okay. But the reason is because if you get rid of that P naught early, you're going to get to a spot where you can't get rid of some of these knots because you don't have that P naught to like cancel out. And you're going to get to a spot like we did in number 6, where we see a lot of like V and V naught and T naught, but they won't line up in a way that you can actually easily solve the problem. You know what I mean? And then what you'll have to do is you'll have to and something with 1 and then convert that 1 into a P naught or P to get that P naught back into the problem in order to solve it. So. All right. Whew. Now, just for everybody out there, Boolean takes practice. I do not expect any of you to be masters of it yet. I've got some math people in here, and maybe you're like, yeah, I got it. It's obvious. I got it. But I'm telling you, I am the lead DE master teacher for the nation, right? And it took me years to feel comfortable with this. Okay. And so you'll get there. Okay. There's nothing wrong with struggling with it right now. It's a struggle. For years, I'd be like, let me figure out, why did I do that? Let me go back and look at my notes. Let me look at the answer key. Why? I stumbled across a website this year called boolean-algebra.com. Okay. And it's a wonderful website. I have not figured out yet how I want to implement it with my students, but they're probably going to find it on their own at some point. So this is the Boolean algebra simplifier. And in theory, you can put in P naught, VST, or PV, or PT, or PS. Okay, let's just put that in. That was like our second to last step. No, let's put some more stuff in there just to be not T, not S. All right, something like that. I did it bad. Sorry. Hold on. That's what I get for being lazy. All right. Anyway, so what it will do is it will tell you not only like what the most simple form is, but it will actually tell you the steps that they would take to do it. So I think this is going to be a really powerful tool if I can figure out exactly how, like when in the curriculum would be right to talk about this. If you bring this in first, obviously they're going to be like, well, I don't have to learn any Boolean now, ta-da. But first of all, the words they use are a little bit different, and the formatting they use a little bit different. But as teachers, I get the feeling that this might be really useful when you're trying to like solve things with kids or help them through, or, work on your own knowledge, because it shows all those steps. That's actually pretty darn cool, which I think is neat. So, okay. All right, gang. So I'm going to give you some tips for majority vote, because as I said, you've got the truth table. You're going to create the truth table for majority vote if you haven't already. You're going to pull this big unsimplified expression if you haven't already. You're going to simplify it, which we just did together, but you got that simplification. Okay. Then you're going to put this into multisim, this circuit we just designed. You're going to put this into multisim. Okay. Now I want to bring up multisim and just give you a couple of tips and tricks for organization. So far, our circuits have been pretty small, pretty simple, but we're going to start to get some much more complex ones. And I want to give you some organizational tips while we do this. So for majority vote, and again, you don't have to follow along because I'm going to kind of cruise through this quickly. I have 4 switches, right? I've got P, I've got V, I've got S, and I've got T, PVST. If you're like the person who would like those all to be aligned, you don't like that it kind of drifts to the left here, if that's the kind of person you are. I just learned last training that under edit, there is an align, and you can align them if you want, align them to the left. So now they all line up nicely. Isn't that cool? I just learned that last training. So there's my PVST. Now you are going to end up with a whole bunch of AND gates and a whole bunch of OR gates. So my first term was PV. So I'm going to place an AND gate, 74LS08. Okay. Now I've talked about this a couple of times, but now it's getting really important because you are going to breadboard, or in our case, Tinkercad, this circuit. So it's actually now it's really important that you pick the right letters here. Okay. So I'm going to pick my first AND gate here. That's going to end up being my PV gate. And then I need another one for PS. Look how I'm grabbing from U1, from this chip. I'm grabbing gates from the same chip. Here's one for PT, PV, PS, PT. Now I need VST. So I'm going to grab this one. This would be like V and S. And they say, Mike, you're all out. There's no more gates left on that chip. So I got to grab a new chip. Okay. Now, organization. There are a couple of tools I want to show you for organization, and I really like them. The first one I don't use, but some people really love it. So I'm going to show you because some people maybe in here, you're going to be like, yes, I love it. And it's called a bus. So if I place bus, it's right here, place bus. You can imagine a bus, like if I click it and double click it, you can imagine a bus like a huge PVC pipe or something that has an infinite number of wires in it. Okay. And so this first switch, this is P, right? So I'm going to take this over and I'm going to connect it to my bus. Now, please, please, please watch carefully. This is really dumb. If I do this, you see how that wire is like straight on connecting to this bus? It will not connect. This is not connected to the bus. When I back it out, you see this little angle? Doot, that means it is connected to the bus. That's counterintuitive to me. But when you see this little angle, that means you're connecting to the bus. When you connect to the bus, it says, all right, cool, buddy. What are we going to call this wire? And we're going to call this wire P for president. Now, what I can do is I can grab another wire and go anywhere on this bus. And they say, what are we going to call this wire? And if I call it P, those two are wired together. And my next term down here, I can grab it and I can say, I also want that to be P. So all three of these wires are connected together. Now what did I say? V. So let me bring this switch over as my vice president. I'm going to call that V. And this one should be V. So I'll bring this over. V. Now those two wires are connected together. I can prove it if I change the net color. Let me double click this wire and change the net color to like purple, pink, magenta, whatever. See, it changed both of those because that's the same wire. Okay. So as opposed to having like spaghetti crisscrossing wires all over each other, the bus is a nice option to kind of consolidate that and keep it neat. So that's the bus. It's okay. It's okay. I like it better than nothing, I think. But I actually prefer a different option. Boop. Similar idea, but it's called an on-page connector. So if I place connector, on-page connector, it's like this little diamond thing. Bloop. What are we going to call it? We're going to call it P. Okay. And then I'm going to place another on-page connector. Place connector, on-page connector. Keyboard shortcut fans, it's Control-Alt-O. What are we going to call it? We're going to call it P. And now those two are wired together. in the real circuit board world, we would call that like a via. They call it where the wires go like through the board and behind, and we can imagine that they're like connected behind the board. And then I can do another one down here. P. And another one down here. P. And V, and so forth and so on. Now, is this a huge time saver on majority vote? Not really. But these tools, as we get our more complex circuits into tomorrow, tomorrow we do our date of birth circuit, these help a ton. Not only just like time savings, but also just I can look at this term and I can say, hey, what term is this? PV, no question. Took me 1 millisecond to look and say, this term is PV, right? I didn't have to trace wires back and what switch do they connect to and blah, blah, blah. Again, you can certainly use color coding if you'd prefer, you know, if you want, you know, this to be V, you can do that and work that out. Okay, we would have OR gates. Again, picking the right gate on the chip. So there's PV or PS, call it. Or PT. Or VST. So like, here's my first two. Cascades into this one. Whoa. When I'm not trying to wire very quickly, I would, you know, move this over so they kind of line up. Okay. So that's the general idea. Now, my other quick important tip for you I mentioned before is these package pin names. I really want the numbers on here. Now you'll notice by default they're not on there. Okay. So we're going to turn them on. You can do this like gate by gate if you double click it. Under display, you can like pick things, but I'm efficient. So I want to go options, sheet properties, and package pin names. Like it has like a square, and that means sometimes. Get out of here with the sometimes. I want all the time. Boom. I want package pin names to be a check mark. Now, when I look at my gates, I see my pin numbers 1, 2, 3, 4, 5, 6, 8, 9, 10, etc. So when I go into Tinkercad to build this thing, I know that pin 3 on chip U1 is going to get wired to pin 1 on chip U3. That was unnecessarily confusing. Pin 6 on this first chip goes to pin 2 on this chip. Okay. I think I have, let me open up Tinkercad real quick. I want to show you some thoughts on how to lay this out on Tinkercad.
Would it be ultimate crazy if the kids wanted to name the chip something else other than these U1, I mean UA1?
Oh, they
Would it
could.
be-
They could. Yeah, they could. What sometimes kids will do, especially as we get the more complex ones, is, you know, whatever they are, U1, U2, whatever, they'll take like little Post-it notes or pieces of tape or whatever, and they'll actually put them on the physical chip so they can remember like this is U1. But to your point, yeah, you can call it whatever you want.
thinking of ways of trying to make it more interesting, probably
Mhm.
gain their interest level.
Yeah.
Giving them a decision.
Mhm. Okay, so here I've got some stuff in Tinkercad. One tip I have, I like to do, here's my, get rid of my labels here for a second. I like to have the AND gates like on either side of the OR gate. Because what kids almost always do is they put down their AND gates first and then their OR gate. And we know that the AND gates feed into the OR gates. And so what happens is you end up with like wires crossing over this AND gate, and then this gets into a huge mess. So my recommendation for that is to put the OR gate in the middle. And that way all your wires kind of feed to the middle and there's not as much crossing over. Okay, so that's just a quick tip. Leave space between your chips because we don't want wires over chips, especially in real life. Let me tell you an absolute law of electronics is if you wire all these wires over this chip like this, tight, and you got wires like kind of holding the chip in like this, I guarantee you that chip's going to go bad and you're going to have to replace it. That's just like a law of the universe is the harder you make this chip to get out, the more certain I am that that chip's going to fail and you're going to have to replace it. And you're going to have to unplug 35 wires to replace that chip. It just happens every time. So as opposed to going over the chip, you want to take your wires around like that. I like to, when I can, keep my wires way up here, like on the far side of this row. So the middle part stays open and clear. That makes your life easier too. So you can see like what I did with this pink wire. Maybe my natural assumption would be to like grab one here and move it over there. But like look at all the crap I'm covering now, right? So the more wires I put in here, the more complex this is. So instead, I started up here, took my wire up into this negative space, over and down, just to keep this as clean as possible as I go. Your switches, don't do this. I was getting cute over here. Don't do this. This is the harder way to do it. There's a slide switch you can use. This is exactly like the switch you have in Multisim. Okay, it's like the switch you guys have on your physical breadboards that you came with your kits, right? Exactly the same. And so I would run one of the legs of my switch to 5 volts. I would run one of the legs of my switch to ground. And then the middle is my data. So this would be like P, right? This is P. And now I'm going to go back to Multisim and say, all right, Multisim, what was I supposed to connect P to? Oh, P connects to pin 1 on chip U1. So I use these little labels and I said, this is going to be chip U1. So pin 1 on this guy needs to get P. Okay, so P, that was here, right here. Okay, so here comes P. P coming down into the negative space, over, boom. I probably won't leave it black. I'll probably pick a different color. Quick tip for you, the number keys on the top of your keyboard, 1, 2, 3, 4, 5, 6, those are little shortcuts for the color of wire. So if you, it's a nice little tip as you're coloring, you know, maybe you pick like, maybe I'm going to say, okay, so 3, button 3, looks like it's orange. That's going to be my color for P. Okay. And then I'll put another slide switch in. And then maybe this will be V. Wired up to power. Wired up to ground. And now this is going to be V. And I'll pick yellow or something. And where's V supposed to go? V is supposed to go to pin 2 on chip U1. Okay, so pin 2, bring it down into the negative space, bring it over, pin 2. Oh, pin 3 connects to pin 1 on chip 3. So pin 3 here connects to pin 1 on chip 3. These are ones that sometimes I'll let cross. So maybe I'll take this one over to there. Nice and clean. Okay. One thing I didn't do that you definitely should do is after you have it built in Multisim, test it. I cannot tell you how many conversations I've had with kids where we're physically breadboarding. They have chips, they have wires. They're asking me to troubleshoot it because it doesn't work. And I go, did it work in Multisim? And they go, I never tested it in Multisim. And I'm like, dude, you're killing me, right? Test it in Multisim. Make sure it works here before we start breadboarding. You don't want to waste all that time breadboarding a circuit that never worked in the first place. Okay. All right. So, what do I want to say? That is most of my tips, I think, for Tinkercadding it. The undo button is your friend. Here's something that sucks about Tinkercad is if I accidentally grab this breadboard and move it, it like does horrible things, right? And ugh. So don't try and move it back. Just hit the undo button. Okay. Iterative saving isn't a bad idea. You can save copies. So like if you have something that you think is you're about to go to sleep or something, you can save a copy. That way you've always got like a halfway done copy that you know works or whatever. Again, more important when we get to our more complex circuits. There you go. Finally, capturing evidence of this working when you're done. How are you going to capture evidence of it working? Two options. The easier / better one is to record a screen capture of this. So run your simulation and click through all your states, P, and then PV0 and PV0 ST and so forth and so on. I like Screencast-O-Matic. Is that this one? Screencastify. Screencastify has a nice little browser plugin. You can just be like, record, and it'll be recording when I can go through my simulation. I believe it actually has like a one-click send it to YouTube. And then in your documentation, you can just put the YouTube link in. That's my favorite because it will always be there. If you go and look at your documentation 5 years from now, that link is going to work and it's going to be great. Okay. The alternative is like a series of screenshots. There are 16 combinations, 2 to the n. And so you'd need 16 screenshots that show me every single state and whether or not the LED is lit up. My preference, of course, is the video. And if you say, Crash, I don't really know how to screen capture a video. Well, you are going to have to do it for circuits we do next week. So if you don't know how, I'm happy to help you figure it out. And you are going to have to do it next week. So there you go. So it's your turn. It's your turn is do majority vote. This is the first time we are doing a beginning to end design, which is pretty cool. And it's actually pretty easy to grade because at the end, did it work? If so, then you probably did all the other steps correct, right? And so when I'm grading this, I'm really just like, it's almost like a checklist. Design brief, yeah, you got it. Truth table, yeah, you got it. Unsimplified logic expression, yeah. And did it work? Yeah. Okay. A reminder for your reflection on this, you can either do it from the student perspective, which is, here's what I learned. Here's what I know now that I didn't know before. Here's the mistakes I made. Here's what I learned from it. Or if you'd prefer to do it from a teacher perspective, here's how I'm going to facilitate this lesson. Here's changes I might make. Here's stuff I'm worried about. Here's what I'm going to have to prep before I do it. Whatever. Oh, last thought. Sorry. If I think somebody asked me about this before, if you have all the materials and you want to physically breadboard this instead of doing it in Tinkercad, that's fine. I don't think you have enough parts and pieces in the kit that Project Lead the Way supplied you. Unfortunately, I think you only have 3 switches and stuff like that. But if you have access to your classroom, if you have all these parts and pieces and you feel like physically breadboarding it, hey, that's fine with me. All right. I'm going to stop yapping for a while. I'm going to stop recording.